So next up, actually I need to just do one little thing because this speaker, this is unprecedented in MLOps WTF. This speaker has written his slides in LaTeX, which I am a big fan of. But now I just have to figure out what I do to, there we go. That's the thing I do. All right. Thank you very much. So Eduardo is going to be speaking about floating point instability and how that impacts AI security and safety. So yeah, I hand it over to you.
Thank you.
Is that on?
I hope so.
It's all done. It's all done, Sam. Thanks.
All right. Yeah, so it seems like it works. It's exciting to be here. Completely different topic from what we just heard about. And yeah, hopefully you're going to see some side of machine learning that you never thought about before. So yeah, I am Eduardo Manino. I am a lecturer at the University of Manchester, and it's specifically in the software and security group. So this will be a little bit about AI safety and security. And one of the problems that we have smashed our head into is that a lot of ML professionals, especially on the data scientist side, try to think of machine learning models and neural networks as some sort of mathematical functions in real values. This is usually all the works from statistics and from optimization, gradient descent, and any sort of work with that flavor. So the real foundations of deep learning starts from this assumption: I'm operating on real valued numbers, which of course they don't exist on the computer, right? So what we are actually doing is working on some finite representation and hoping for the best. And there will be a lot of this hoping for the best in this talk, which is fine for most machine learning applications, but a bit less fine for security applications. And of course, I mean, you must know, since you do MLOps, is that it's not just floating point, but people are trying to do some sort of extreme quantization with just very few bits. So this problem gets exacerbated. So how much is a problem? So I'm telling you it's a problem, but maybe we can put some numbers. So the problem really happens after the training. So for this whole talk, imagine that you have trained your machine learning model and you're really at the deployment stage. So the question here is, how much does the machine learning model change before and after deployment? Or to think it in a more correct way, how much does it change deployed on the data scientist platform that was used during training versus the production platform that is actually doing the inference at scale? And of course, there will be different devices over there. So CPU, different kind of GPUs, maybe a TPU if you want to be fancy. And maybe if you're doing very large scale, this is distributed over multiple servers, or maybe very, very non-transparent Amazon machines, right? And people have worried about this, and they've measured. So one of my hobbies is collecting these papers. Every few years, somebody, usually from the machine learning community, tries to measure this difference after deployment and puts out there some numbers that then I show you, and then it gets ignored. And then a few years later, somebody else does the same work, usually without citing the previous people. So in the worst cases, so the worst reported numbers are on image classification models, and they have observed up to 6% accuracy fluctuations. For image classification models, this is pretty bad because at least a few years ago, you could claim you're doing state-of-the-art just by improving those models by 0.5%, right? There was a bit of a race. Now everybody's talking about large language models, so that race is over. But still, you could have a state-of-the-art image classifier, deploy it, and suddenly you don't have a state-of-the-art image classifier, but actually you have instead something fairly poor. And the question is, what is exactly going on here? Some of it is actual hardware. So noise introduced by the camera and maybe the JPEG compression. But some of it is actually happening really inside the neural network or the classifier. And this is all the algorithms that do matrix multiplication and convolutions. They are heavily optimized, and they are heavily non-deterministic. Part of it because of parallelism, part of it because which exact algorithm is running on your GPU may depend on how hot the GPU is at the moment, right? So if the GPU is very hot, maybe you will switch to a less optimized algorithm or something like that. So your performance may change even on the same device. One thing that a PhD student might notice fairly recently is that results change if you change the batch size, even at inference. So the outcome of your classification on item 1 will be affected by the fact that in parallel, you are also trying to classify item 17. And changing that batch size is going to make the slides disappear. All right. So this is happening. So this is happening on your device, on your phone, on your pipeline. And again, for most applications, it's fine. If you're doing a recommender system, probably nobody cares. But now I'm going to go a little bit more into applications where instead this matters a lot. And so I'm going to force you to think about floating points. And this is the application. So imagine you have some, let's say, safety critical applications, some industrial machinery or something, where you really need your neural network to be monotonic. This is a classic requirement in industrial application. For example, you're running an anomaly detector, and you know that if the temperature increases, then your probability that there is an emergency definitely does not go down, right? All right, so now you need to build this thing, and you probably do, okay, to take a multi-layer perceptron and make it into monotonic by design, you're probably going to set all the weights to some positive numbers, and you're going to choose activation functions that are monotonic. If you do those two things, you are for sure creating a monotonic function to a point. Because then somebody, maybe an MLOps engineer, decides that your monotonic functions are not very efficient. So maybe you're using hyperbolic tangent, and they say, well, why don't you switch to soft sine? That costs less, it's a bit faster, and it will be very helpful because we are deploying on a microcontroller that does not have support for hyperbolic tangent, but it can do multiplication and division, so it's fine, right? So now we're going to retrain a neural network, but this function is still monotonic, and so it's OK. We still satisfy our requirement. The question is, but is it? Right? Because now we are, in real value, yes, it's monotonic, but now we are doing floating point. So what I'm going to ask you is for 20 seconds to think about whether that function implemented with that code is still monotonic. I'll answer the easy one, and then I'll let you answer the difficult one. So first of all, it's not monotonic anymore at infinity. Okay? So if you use hyperbolic tangent, it will converge to +1, -1. If you do that, you're going to divide infinite divided by infinity, which is going to give you some not a number, right? So, but again, this is probably out of the operating range, so it's not of a problem. What about the rest of the function? Is it still monotonic? Does anyone have opinions on this? Let's see who's the floating point wizard in the room. There is usually always one.
It's been too long since I read there's that paper, What Every Programmer Should Know About Floating Point Numbers. It's been far too long since I read that, but I recommend it.
All right, I'll give you the answer.
Depend on the architecture, won't it? And
it depends on the architecture. Okay, assume this is IEEE 754 32-bit floating point, which is the industry standard. It's what PyTorch gives by default.
Now, hang on a second, because is it not the case that there are values of A such that simply 1 plus A is going to loop around? Is that the case?
No, floating point does not have wraparound overflow. So overflowing floating point will go to infinity.
Yeah.
So luckily we don't have that problem. But you have that in quantized neural networks. All right, I'll give you the answer. A bit all over the place. So this, I'm going to show you one example, but this happens throughout for any value of the input. You have this effect, which is the numerator and the denominator are gonna round at slightly different points. So there may be a case where I increase the input, the numerator does not change, but the denominator does. Therefore, the function decreases by a tiny amount, but it does decrease. Now, the problem is, if you are in the last layer and that tiny amount is multiplied by a very large weight, the output of your monotonic neural network is not monotonic anymore. So more pressure in the system makes the neural network think it's more safe. Sometimes. Right, so this is an extreme case. There have been accidents in the past where tiny floating points error have made missiles explode and sometimes kill people. The problem is that from the industry perspective, apart from the fact that we don't want to kill people, we also have legal requirements that force us not to kill people. This is the EU AI Act, but now many countries around the world are putting together legislation that's sort of the same. And they have a laundry list of high-risk AI system. This is your usual stuff, so military applications and aerospace, but also things like law enforcement, assessments in schools, access to services, banking, things like that. They are anything that may touch the personal rights of people becomes high risk. And for that, there's a very high standard. Now, for the EU AI Act, they tone it down a little bit. In the draft, it was like, you need to do exhaustive testing for all possible inputs. Now it's just do as much testing as possible, be as resilient as possible, without telling exactly what they mean. Lawyers are amazing. But you can imagine that if it is actually a neural network deployed on an airplane, you probably want exhaustive testing, right? Which brings us to this problem, which is we cannot guarantee that a model is safe. Just it doesn't mean anything that a model is safe. The only thing we can say is this specific implementation running on this specific hardware at this specific time is safe. And so all focus in AI safety needs to switch on checking the final implementation, the production version of it. And how to do that with the current technology is really tricky, to the point that it's almost impossible. So what I'm going to do now is give you very quickly a partial solution. Like if you want to achieve this super rigorous standard of safety, what do you do now? So you have some way you have to go from the machine learning model to an implementation, and that implementation needs to be portable. So no matter where you deploy it, it needs to give you the same result, because you want to deploy it in a testing environment, do your testing, prove it is safe, and then move it to the production environment, and it does not need to change. So very extreme. First of all, don't use PyTorch. Don't use any framework, ever. Plain old C, or any code, standalone C. No libraries, just code. You can use Java, whatever, as long as it's some code with very clear semantics. There are frameworks that target microcontrollers, which use this not for the portability, but because they need the microcontroller compiler. So we can hijack them and use them. But again, they are thought for very small scale applications. Yes, no call to the mathematical libraries, because the mathematical library has semantic ambiguity. So that you achieve portability, of course, performance hit, so no parallelism, no nothing, no optimisations. Right? Now you have a portable implementation, which will look like a file full of C and full of arrays of values. Horrible. Yes, and this is just a snippet of a very small neural network. But anyway, so you have that, and that is portable to a point if you're being careful. And then you need to test it, right? Which means you will have your code that describes what the neural network is doing, and then you will have your safety requirement, and now you need to have something that tells you whether the requirement is satisfied by the neural network. And of course, the normal thing to do is to do testing, but again, we want to have a super stringent standard. Testing will only find bugs, which is great, will never prove it safe. We need to somehow do exhaustive testing, which, well, if you have more than one input to your neural network, it's impractical. You cannot brute force it anymore. And so the only thing that is left is something that some of you might have never heard of, which is formal verification. So now we go into real crazy territory. So the idea is that you somehow build an algorithm that is able to automatically produce a mathematical proof that that safety property is satisfied for all possible inputs. And the system you're trying to prove this thing about is a random piece of code full of floating point calculation. So the only existing way to do that right now on the market is called a software verifier. So it's something that takes as input a bunch of code and a safety properties and is able to tell you, sometimes is able to tell you yes or no. Luckily for me, one of these software verifier is developed at the University of Manchester. And so from now on, I'm just going to show you results with this software verifier. But of course, the big problem is realizing how feasible is this procedure. So we already have lobotomized the neural network and turned it into a piece of C code. Now we're going to do something very niche to try to prove its safety. So I'm going to be the good scientist. So first I introduce a benchmark and say, aha, I have to measure. So let's measure. This is my metric. There's about 900 different pieces of code with a safety property. About half of them can be proven safe, and half of them have a bug. And now the question is, can state-of-the-art software verifiers actually solve this? And then you can see that at the top, we have maybe just one activation function, so it will give you exactly the problem I gave you. So here's just a soft sign. Can you prove it's monotonic, right? So it's a very small problem, up to here's a full neural network that's trying to do reinforcement learning. Can you prove that the robot never crashes? Large-scale problem. And this is a very, very tiny graph. But you can see in yellow are all the benchmarks where even after 15 minutes, the software verifiers gave up. And then the small bars is the ones that have been able to prove safe or find a bug. Right? And this is a state-of-the-art model checker. And of course, we repeated this experiment for many software checkers. This one is the best in the world right now. So it's a very depressing picture, which means you will never be able to prove safety with current tools. So what are we going to do about it? Well, first of all, we need to throw away all the existing machine learning infrastructure and replace it with something that is actually portable and reproducible. And so that at least we have a chance of proving safety. And then, of course, we need better verification tools, and we are working on that. There are even competitions around the world. You can imagine this is usually academic groups with some companies. And each of these competitions has probably 15, 20 tools competing. And the big problem is and always be scalability. So right now, we are at the point where maybe for this industrial application, with a very small neural network on a microcontroller that is making sure that two airplanes don't crash into each other, we have a chance. Your big image classifier, making sure that we'll never misclassify a panda into a car, never going to happen. Okay. So that's the sad state of the world, and a little bit of what we're trying to improve it. Thank you.
I mean, that was fascinating. I've got two big questions before we go to the audience. One was, so the example you gave was really interesting, but also quite niche, where you have maybe an MLOps, you have an application that needs to be deployed to an embedded system. You have an MLOps engineer who realizes, okay, this hyperbolic tangent can be re-implemented using soft sign. That's a very nice optimization. I would suggest a lot of people doing MLOps, we're probably not thinking about microcontrollers and they're not thinking about those optimizations. But for those who are and are doing safety critical applications, the thing that worried me was, how on earth do you ensure that those engineers know the dangers of an optimization like that? How do you educate?
So the optimist in me says that most of these engineers are embedded in industries where safety is a big thing, like aerospace. So that's a good thing. They're not never going to deploy something that is unsafe. The bad part of it is that, therefore, they are never going to use machine learning.
Yeah.
So until we have a pipeline and tools that can create safe neural networks, aerospace industry and automotive will never improve.
Yeah, that makes sense. And then I suppose because this is obviously what your research group does, what if people in here want to contribute to that effort or want to kind of get involved in developing better tooling, trying to solve some of these challenges? Any thoughts on how people can do that?
Well, so first of all, be aware. Be aware that your beautifully trained machine learning model can actually perform differently once you deploy in a different device. And then, the answer to all of this is you need to study formal methods, which is, again, a very niche topic that, as machine learning people, we are not used to even consider. There has been a revival of the topic because of these safety issues. So now there's more people that are toying with theorem provers and formal languages, and even now something like Rust is becoming a thing because people realize memory safety is critical in software. So we need to have the same decade-long shift in mindset in the machine learning community. That's it. It's gonna take time.
Go ahead, Anthony.
I've had a career of 40 years of software. System safety is a passion. 1989, working in a nuclear power station, we tried to use formal methods to prove we did not lose an alarm. Took us 6 months to 20 lines of code. It's not scalable when I've got millions of lines of code in a car these days. So I totally agree with it. Really good, fascinating thing. Great in Manchester's a lead. Great. Novel Manchester, great. But how do we get something that's scalable? Because actually, picking up most engineers, even in embedded spaces, safety is not their paramount. Their job is features and get their milestones done. And someone else's problem to prove it's safe and secure, the safety engineers and security engineers, who are doing the paperwork, because essentially that's what it becomes. So how do we bridge the gap? Because to me, AI could be the helper, but we're actually saying AI is actually the problem. How do we help? How do we get AI and safety and security to work together to break the thing that's been a panacea for 40 years, and we haven't really got anywhere. We haven't been educated in computing technology to solve it. And it's great to see what you're doing, because I know you made some great steps.
What do you think to that?
So I have three things to say. So first of all, yes, nuclear industry is one of those safety critical industries where people actually care. So thank you for being part of that. Second, formal method scalability has improved since 1989, a few orders of magnitude. So there are attempts at verifying autonomous robots, and there are attempts also in at the nuclear authority here in the UK and in France especially, to have some guarantees, at least on pieces of the system, right? And in terms of education, like you can't. This is the old age problem of safety education, right? Cultural shifts take time, and yes, in nuclear aerospace, we have done these shifts, but it took generations, right?
So the software is 40 years old in that.
Yes,
It's
and
not changed, it won't change because it's hard to change.
absolutely. But machine learning is still a relatively new thing, and all these, we throw away machine learning frameworks every number of years. Now we're throwing away TensorFlow, nobody likes it anymore. So there is a chance of, getting into one of these cycles and doing things a little bit better, but it's multi-billion efforts, right? So.
I think we'll do two more. We're running slightly over, but how about we'll start with
Me?
Oh, yeah, go ahead. Yeah.
I mean, I am not sure how to explain this, but I wonder if the problem is not computers and the limitation, or math, but if we need to do something, because, I mean, if you think about functional programming, you usually think, is this function pure? Is not, because if you receive a integer and if you return an integer, many things can happen, right? It's not real a pure function. So in the case of when you think a paper, you see in the domain of real number, and usually you see every time only if x is greater than 0. I wonder if the papers need to be if the decimal point is not greater than and the paper needs to be based on those limitations. I mean, because that is the problem when you think, oh, this is math proved. No, but the computer is not math. So I wonder if the paper should be computer oriented, not pure math, because
Not enough. Because one thing I haven't mentioned today is that also the hardware may go wrong. So you do your floating point computation and one bit has been flipped, right? So how do you protect that? So it's really the full pipeline down to the chip.
Yes, so your monotonic floating point function could be non-monotonic if a bit gets flipped by a cosmic ray anyway, right? But also, because I was thinking when you said that, I was like, oh, actually, should we just do fixed point computation anyway? That still doesn't solve the problem, but at least it gets rid of some of the weirdness, right?
Yes, that has been the attitude of the safety critical industry all the time. Like you just don't use floating point. The problem is floating point is such a core part of the machine learning pipeline now that it's really difficult in some application to get rid of it.
Indeed. Who else? Or who am I gonna? I'm gonna go here, and maybe we can do both.
Really nice talk. I guess my main question around it all is, where's the room for risk acceptance? And kind of saying, well, what we're currently doing is so inefficient or already risky, and so comparing our current solution and saying, well, actually, it's 99.9%. We're sure it's better in these cases. I know that the EU AI Act there is saying, no, we have to formally verify those things. But do you think that, as someone who talks things about this quite a lot, in the future there might be a case where they say, well, actually, no, we just need to prove within certain bounds, even in high safety critical systems, no, it's accepted risk because of the risk of not using these systems?
So yes, and the legal frameworks are moving towards this more ambiguous language of reliable as much as possible, something like that. Also, yes, sometimes an AI component in, let's say, an autonomous robot is seen as long as it keeps 95% accuracy, then I sort of find ways to compensate for the 5% times it goes wrong. The problem is that even if you allow for this sort of probabilistic requirement, then you also need to check that. So you claim that this neural network is 95% accurate, on that specific benchmark. But is it still 95% accuracy in the real world? And probabilistic verification is more difficult than the verification I showed here.